Vale. Okay, next speaker of today finally is Ángel González-Prieto from Universidad Complutense de Madrid, and he will speak about generative adversarial networks for mathematicians.
Thank you very much. Thank you very much for the invitation. It's a pleasure to be here and to be here with all these people that want to know so much about machine learning. So first of all, I want to apologize because I am not a machine learning engineer. Actually, I am an algebraic topologist, so I am not even an analyst, but I try to do my best with all this stuff. Today I want to talk about generative models. Generative models, the idea is that you have some phenomenon that you want to understand. It's a phenomenon that is very, very complex, and you want to replicate it. For instance, you want to create faces of people, and what I want to talk about today is about a model that is able to generate these pictures. These pictures are pictures of people that doesn't exist. These people, these are images that have been created from the scratch. Also these pictures. So the models are extremely impressive, and they are called GANs, Generative Adversarial Networks. And the idea of a GAN is that you have two functions that are going to compete. And how are they going to compete? They are going to compete because one of them is going to be a discriminator. It's like an expert in art that is going to say, I think that this is a real image. This is an image from a real person or not. This is an image from a fake person. And the other function, G, the generator, is going to try to generate samples that confuse the discriminator. So the discriminator is going to be exposed to two different kinds of samples. The first kind is real samples. And for these samples, D has to say, okay, these are real samples, this is real people, and also it's going to be exposed to fake samples, and it has to say, no, this is not a real image. And they compete because D wants to be very, very competitive, wants to be able to discriminate between real samples and genetic samples, and D aims to confuse D, aims to create samples of such a quality that D is not able to discriminate between real and fake samples. And how can we formalize this idea? Well, we can formalize this idea through a cost function. And the idea is the cost function is a function that depends on the generator and the discriminator, so typically, the generator function and the discriminator function are functions that depend on some weights. For instance, they are neural networks, and they depend on the weights of the neural networks. And the cost function is what is the error that D suffers. So if we put the convention that D equal to 1 means that the discriminator thinks that the sample is real, and D equal to 0 means that the discriminator thinks that the sample is fake, then if you look at this is exactly the cost function. You want, on the set of real samples, you want to optimize this term, you want to maximize this term, and on the set of generated samples, you want to minimize this term or maximize this term. Okay? So the aim of the discriminator is to improve this function, and the aim of the generator is to decrease this function. And this is why this is called the GAN game, because there is a competition between D that wants to maximize this and D that wants to minimize this. And the aim of the training of a GAN is to find a Nash equilibrium, which means a point in which D is not able to maximize this function only in the direction d, and g is not able to minimize the function only in the direction g. And this problem has a very nice probabilistic formulation. And it's actually due to Goodfellow, which was the guy that first formulated this problem. The idea is, if you suppose that your sample that you want to generate and the sample that you actually generate are continuous random variables, then you can write down the cost function as this. And if you pick G and you want to optimize in D, then you have to optimize this function. And you can optimize this function by arguments of calculus 1. So at the end of the day, you get that for fixed G, if you fix G, the optimal generator is this guy. And this guy is the density function of X divided by the sum of the density function of X and the density function of G. Okay, this is the optimal generator, the optimal discriminator, sorry, this is a typo, the optimal discriminator, but this is a theoretical version, but this is not feasible in reality. Why? Because you don't know the density function of X. So okay, this is a very nice theorem that is absolutely unusable. But it gives you an interpretation of the cost functional of the GAN. And the idea is that if you plug the optimal discriminator here, you plug it here and here, and you compute what is going on with the cost functional, you have to do some substitution. You have to put 1 half here and a 2 here, blah, 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 blah. And at the end of the day, you get that the cost functional can be written as a constant minus log of 4 plus the Jensen-Shannon divergence between X and G. So for a fixed optimal discriminator, G aims to minimize the Jensen-Shannon divergence between the generated sample and the real sample. And this is the probabilistic interpretation of this problem. I recall you that the Jensen-Shannon divergence is nothing but a distance in the set of distributions. Okay, it can be written in terms of the Kuban-Leibler divergence, which is this guy, and blah blah blah. But at the end of the day, this is a distance between two random variables, and G aims to minimize this guy. So this analytic game has a probabilistic interpretation, and this is the interpretation that Goodfellow provides in the paper. So now, looking at a more practical point of view, what can you do for improving these functionals? Well, what you can do is D wants to improve the functional F, and G wants to decrease the functional F. So you apply gradient descent and gradient ascent in the direction of D and descent in the direction of G. And this is actually called alternating gradient descent algorithm. And this is the algorithm that people use for improving, for training this guy. You improve the parameters that define the discriminator and the generator by improving D with the plus the gradient and decreasing G with minus the gradient. And typically, you cannot compute expectation, because if you look at the definition of the cost functional, this cost functional has some expectation in the real random variable and some expectation in the generated random variable. So what you have to do is to sample it. You have to draw a sample and to compute the expectation just by the typical mean. And in that way, you can write down the gradient of this cost function in terms of the gradient of the discriminator, with respect to its parameters, and the gradient of the discriminator and the generator with respect to its parameters. So at the end of the day, this is something that typical libraries in machine learning are very good at, to optimize neural networks depending on its parameters. So you can actually go to TensorFlow or Keras and to implement this algorithm. There is actually a very nice theorem which says life is very, very happy because the critical points of this scheme are locally stable, meaning that the Nash equilibrium of the GAN game attracts orbits. But this theorem has hypotheses, and the hypotheses are not true in reality. The hypotheses are the perfect discriminator has to be implementable, the perfect generator has to be implementable, and this is something that typically you cannot do that because, okay, neural networks are very good at approximating things, but approximating, not nailing. So it's unfeasible to be able to create the perfect discriminator and the generator. You also have a technical condition regarding cost functions, and you also have a condition in which you say you also have to be able to approximate the support of the right support of the random variable, not only exactly at the Nash equilibrium, but also in a neighborhood. And this is a problem. So in reality, you get a very bad convergence. Actually, if you want to create something like this is a random variable that takes several different values in a grid. You would like to expect, you would expect something like this. You start at an initial point, you start creating things are a mess, but at the end of the day, the GAN tries to create this ring, and at the end you get the sample. Okay, this is your hope. But reality says that you are not going to get that. You are going only to be able to create big points. And this is a problem that is usually called mode collapse. The GAN collapses at a point and is not able to generate all the diversity of the random variable. Okay? Also, there is a very explicit GAN, a very specific problem called the Dirac GAN, which shows that even in a simple case, the GAN can be non-converting. Okay? So in reality, this theorem is too restrictive. So what can we do? Well, first of all, what is the problem here? The problem here is that we are dealing with a different ordinary differential equation that we would like to. Typically, in machine learning, you deal with gradient flows. You have some function and you want to optimize this function. So you move your parameters either in the direction of the gradient or in the opposite direction of the gradient, but all the parameters in the same direction. But now here we have the Nash flow, in which you move one parameter in the direction of the gradient and the other one in the opposite direction of the gradient. And it's a problem. This flow has very good geometric properties. Actually, this flow has been used a lot for topological arguments. This is the key point for proving Poincare conjecture. But this flow is a mess. Actually, in this flow, you can have centers. You can obtain periodic orbits, and periodic orbits does not appear in gradient flows. And also, this is an example of your problem. If you have periodic orbits, you cannot expect to converge to the optimum. Okay? And okay, well, it's true that periodic orbits does not appear in reality, but you may get something like this. This is a real picture of the flow of a GAN, a toy GAN of a GAN. A toy GAN has two parameters, but it's a real GAN. And as you can see, the equilibrium are stable, are locally stable, but there is a vertex around this equilibrium. So converting with a numerical scheme to this point can be very hard. And this is the problem of the reality. The theorem applies for continuous flow, and in the practice you apply a discrete scheme, and you may have problems with the convergence rate. So what can we do? Well, there have been written a lot of papers trying to solve this problem. And well, there are more or less some interesting heuristics that may work or may not work. But recently, we have proposed a different approach that seems to work. It has some gaps that need to be justified theoretically, but it works. And the idea is that let's help the generator. How can we help the generator? Using something called a Smirnov transform or a probability interval transform. And the idea is very, very simple. It's something that is taught in probability 1. The idea is, if you have a random variable that has a continuous increasing cumulative probability function, then if you compose the random variable with the cumulative distribution function, you get a uniform distribution. And how is this useful? Well, because you can now do the trick in the other way around, and you get any distribution that you want. So if you have some random variable and you want to generate another different distribution, what you have to do is, okay, I compose my random variable with the cumulative distribution function. Now this is an uniform distribution, and I compose it with the inverse. So I now get my ideal probability distribution. Okay? And that's all. A point here, you can have here any distribution. This f has not to be continuous, but you have to interpret it in the quantilic sense. Okay? So at the end of the day, you have a GAN with a generator, and you want to generate another thing. What can you do? You can look at your samples, estimate the cumulative distribution function by using the empirical cumulative distribution function, which is just a nice way, a fancy way of saying the histogram, the sum of the histogram. So you compute the sum of the histogram, and now you can try to help the generator, but instead of using as the last activation function of the last layer of the generator network, using a linear activation function or a sigmoidal activation function, by using an activation function that aims to generate the ideal distribution, the empirical observation of the distribution. And what is the initial distribution that you have to put? What is the initial distribution? Well, if you look empirically at what is the distribution that GANs tend to generate, I'm going to show some examples. They tend to generate normal-like distributions. So GANs are very bad when they try to generate non-normal distributions, distributions with finite support, compact support, distributions, discrete distributions, distributions with a long tail. They are very bad when they try to generate these functions. They usually generate like a bell. So you put as the activation function at the last layer of the neural network, the generator neural network, the Smirnov transformation, the transformation that transforms from a normal distribution to the observed empirical distribution. And you know that Glivenko-Canceri theorem says that you have convergence of the empirical cumulative distribution function to the real distribution function, so this makes sense. And 5 minutes, okay, perfect. So what is going on? You have here this original distribution. This is the distribution that the generator of the GAN usually generates, like a normal shape. And you now apply Smirnov transformation, and you may get something like this. Something which is very, very crazy, but is the reality. This is what the real sample does. And now you are able to bend the curve from the normal distribution to this very, very weird distribution that is actually the right distribution. And it works. In the sense that, I don't know if you can see the pictures, but the pictures are very, very nice. This is an experiment by trying to generate four different features. So our images have 4 pixels, and the pixels are distributed in a very, very hard way. The first one is normal, the second one is discrete, the third one is like an exponential function with non-support for negative numbers, and the fourth one is a Poisson distribution. And if you look, the red histogram is the histogram that a typical band obtains. The blue distribution is the distribution of the real sample, and the green histogram is the histogram of a GAN trained with this Smirnov activation function. And maybe you cannot distinguish between the blue and the green because they are very, very close. So the solution is very, very good, actually, like this. With this Smirnov transformation, we are able to replicate the discrete behavior, and the typical GAN is not able to replicate the discrete behavior, for instance, or this. Okay? And also, just to finish, there are also other quality measures that you can apply to study whether your GAN is converging or not. For instance, you can compute the LP distance between the empirical cumulative distribution of the real data and of the generated data. So you expect this distance to decrease. If the GAN is learning something, you expect this distance to decrease. And also, you can say, okay, I'm going to use my generated data for training another machine learning model for another task. And I want to check what is the performance of this nested machine learning model. So if the data that I generate is very good, then the machine learning model is going to learn very good. And if the data that I generate are not quite good, then the machine learning model is going to be very confused. And you can compute the F1 score, for instance, the performance of this model. And this is the last slide. This is what is going on with a classical GAN. The L1 distance is very noisy and does not converge very well. The F1 score is stable and cannot be improved. And with this Smirnov GAN, this GAN with an activation function given by a Smirnov transformation, then the L1 distance drops quite fast actually and quite stable, and the F1 scores improves and reaches a maximum, and actually this maximum is more or less the maximum that you obtain if instead of training the machine learning model with generated data, you train it with real data. And okay, there are some future problems that can be addressed, but I'm not going to talk about them, and that's all. Thank you very much.